Alright, Assalamualaikum and good afternoon everyone. Thank you for your time to attend this training session. So this training is on battery energy storage system, BESS, BESS. So in this comprehensive training, we will talk about architecture of the battery, and then we'll go into the safety of the battery. And after that, we'll go into the integration of the battery to the grid, to the electrical grid. And then we will talk about the techno-economics of the battery. Alright? So to cover this, we will have 4 modules. Now, before we proceed, let me introduce about me. My name is Fairouz. In short, you can just call me Fairouz. I am the lecturer from the University of Tun Hussein Wan, Malaysia. My department of is electrical power engineering. My background education, I graduated from the University of Queensland, Australia, on electrical engineering. My professional affiliations is I am a professional engineer under the Board of Engineers Malaysia. I'm also member of IEEE, which is organization based in America. Also, I'm a member of MySet. This is Malaysia institution of technology, and I'm also the the energy manager for the university. All right, and regarding my research expertise is I'm mainly doing on the condition monitoring of high voltage equipment, transformer, rotating machine, diagnostic of these high voltage equipment, and also energy management. Now, for this training session, we will have 4 learning outcomes. This is our main. This is our main outcomes. What you will get after this training session. One is on the hardware and chemistry of the battery, which is to identify the primary physical components of modern BESS. Okay, throughout this session, I will just simply call BESS for the battery. Alright, if I use BESS like this, I'm BEST, good. Okay, if without this, then BESS the battery. Alright, okay. And then we'll go into, so you need to also able to evaluate LFP versus NMC. So right now,
F what?
okay, we'll keep that later. So right now you don't know what is LFP and NMC. And then the cell chemistry. So that is the basic. That is the first outcome, learning outcome. Second is we'll go into the safety, if you can remember. So the second outcome is to evaluate the battery management control. SOC, SOH. So at the moment you do not know what is that, right? And then you need to design mitigation strategies if there is a thermal runaway. This is related to safety. Third objective or third outcome is to analyze. Alright. So in the end of this training session, we expect that you're able to analyze the strategies for both front of the meter and behind the meter. Right? So FTM and BTM. Right? And then finally, number 4 is to on the sizing economics, so you'll be able to calculate energy capacity requirement. This is also important. You want to employ BESS in your system, in your university, in your factory, in your industry, right? You need to know the energy capacity, how big you need to choose to purchase for your application, okay? Because you buy too big, too expensive. Too small, you cannot serve the purpose, right? So degradation and then the costing return on investment. All right. So to cover for all these 4 outlines, 4 outcomes, we have 4 modules, 4 outlines. Number 1 is architecture and fundamentals. Number 2 is battery management and safety. Module 3, grid integration and application. This is where we'll cover the front of the meter, behind of the meter, right? And then number 4 is sizing the project economics. Okay, of course, when you want to have investment, when you purchase this battery, these are extremely expensive battery, cost millions. Depends on the application. It can cost millions of ringgit.
Yes.
Right? So we expect that the return, we have to design so that the return on investment is within the reasonable time. Okay, not 30 years. Okay, it's not that's not good enough. All right. So that is the course outline. This is what we are going to achieve for today's session. So before we proceed with the content, with the module, let's do some ice breaking. So we need to know each other. So first, can we hear from you, with our first participant?
Okay, my name is Abdullahi Butar. I'm a Nigerian. I work with Federal University Yousof in my country.
Okay.
I'm a student here, PhD student under the supervision of Professor, Associate Professor Shamsul Azad Zulkifli. And my research is also battery is part of my research.
Oh, that's great.
Yeah.
So, okay.
That's why my supervisor asked me, because my research has to do with AC and also DC, connection between AC. That is, we have a diesel generator, so we have battery. So we are going to have like a grid under a ship. So so we are trying to design the DC distribution system for a ship.
We have previous student from Nigeria, intern student. He told me that in Nigeria, in terms of the battery application, is quite a lot, especially even in residential, even in houses, they have used battery.
We are using it in Nigeria.
All right.
And because we use solar a lot.
Okay. So in that case, when we ask you about what you understand about battery energy storage system, I believe you know, like in terms of the level of the understanding is about, you can say, medium, intermediate, not the beginners. You know, so maybe you have done some project previously.
Yeah, during my masters, I have done some project, but it's under prediction. It has nothing to do with battery.
Okay. All right.
So now I'm going into the battery, my PhD research.
Okay, that's great. So it's good that you have this, you attend this training session. Hopefully this training session will cover the whole aspect of the battery project. Right, not just on the AC DC part, but also like install, safety as well, and also how the costing, right?
All right, thank you.
And how about you? Maybe you can tell us about yourself, your understanding on the battery, right? Name, your professional, your background.
My name is Tom Chai, and I'm the master student of the education. And now still unemployed, and I attend this course to explain my knowledge about the battery energy storage system test, learning more about how to design or criteria about the battery system.
Okay. So before this, I suppose this is the first time you attend any training regarding the battery, Before this, what do you know about battery? When let's say when we talk about battery, what is the first thing you come into your mind in picture? So like,
the battery is using to store the excess energy or as a backup energy when the power is shut down like that.
Okay. That is for you try to imagine, is it the house or your phone battery or your remote TV remote battery? What do you imagine when we talk about battery?
It as a standalone source that can provide energy to the device to control it like that.
Okay. So I think your scope or your view at battery is very wide. general that store energy. How about you?
Yeah. Okay.
Maybe.
My name is Wahyu. So some of you already know me. So I'm lecturer at ETSM in Madya. So I come here to extend my knowledge now for the storage battery because if I already read about this, but usually the battery is only for low capacity, isn't it?
Okay.
But I read in some literature like US and some other country they already install battery with very big capacity. Because I want to know what the detail of this.
Okay, our new participant, maybe you can introduce yourself, your background. William, please.
My name is Mila Rahman, electrical engineering student. This month, Sergi.
Okay, so what do you know about battery? When I ask you, do you know battery? What is battery? So what is the first thing that comes into your mind when I ask you about battery?
Battery is used for storage, energy storage, also for supply.
Alright, this is like in terms of physical. How do you view the battery?
There's two types of battery. One lithium, the other one is like chemical.
Okay, alright. And how about you? Your name, your background, and what do you know about battery?
My name is Usman Malani, from Sudan, electrical engineering student, third year as Mujahid. And the first thing comes to my mind when I hear the battery is the cars batteries. I think it's the chemical, right?
Okay,
And
yeah.
then the small lithium batteries for the small use.
Okay, okay, interesting. How about you?
Okay, my name is Mohd Ahmed. Happy to see you today. I'm also an international student here at UTHM, taking my internship at UTHM. And first thing comes to my mind when hearing batteries is the capacity of the battery.
Okay.
So it depends on the type of the work we need it. If we need it in a hostel, if we need it in a car, if we need it in a company. So what is the type and what is the capacity of the battery that we are going to use in this concept?
Okay, all right, thank you. So I see that we have a wide view of battery, right? Now, here when we use the term BESS, battery energy storage system, what battery is store energy, right? But if you just use the term energy storage system, okay, you can store energy not just in battery. There are other methods you can store energy as well, like pump storage. You pump water to the on top of the hill, so the water stays there on top of the hill. That water is storing the energy in terms of potential, gravity. When you release the water, it will give the gravity. You can move the turbine. That is also energy storage. Even the capacitor, it's not a battery, but it can also store charge, store energy, some energy. So they are, in terms of, if we use the term energy storage, very wide. It's very wide. But when we use the term battery energy storage system, that narrows down our scope. That we are using battery energy storage system. So in this training session, we will go narrower. This battery energy storage system is for what application? Okay, not battery, not for TV remote, battery not for electric vehicle, right? So this is battery energy storage system for electrical power system, right? Electrical power system, which is, I would say, quite, in Malaysia is quite new. Once we have a lot of solar system, now we encountered another issue. Okay, now we have a lot of solar power. It comes into the grid. Solar power introduce another issue, that is surplus. That is something else. So this is where we come to this technology, battery energy storage system. Alright, so now let's go to the first module, BESS architecture and chemistry. Okay, before that, I forgot to throughout this training session, I have prepared some learning activities. So one learning activity for each module. So we have 4 modules. We can discuss later on. Alright, so we'll go through this activity, each of the activity after we finish each of the module. So let's go to the first module. First module is on BESS architecture and chemistry, the fundamental of energy storage, right? So in this first module, we have learning outcomes. Okay. So by the end of this module, what we want to gain is we must able to explain the core function of the battery energy storage system, the function of BESS. And then once we know the function, we have different technologies of the battery, LFP and NCM. So we need to know which one to choose, which one is suitable for your application. So compare attributes. And then the third one, explain physical hierarchy of the battery energy storage system. So these 3, right? So the big picture, why the grid needs battery storage. So battery energy storage system act as a critical buffer between power generation and load, capturing energy for when it is most needed. So of course, in terms of power supply, at the moment, we as load or consumer, we turn on the switch, we turn on the lights, we turn on the aircon, which is still considered small load. But if you go to the industry, to the plant, manufacturing plant, they have bigger electrical loads. So when you turn on the switch, you require instantaneous energy, power. So who is going to deliver this power? Definitely the power generator. Alright? Power generation. So now if you put yourself into their perspective, in their situation, they have to cater your need. Suddenly the demand is increased. They have to increase more power, generating power in their power generation. So that's the problem. It's difficult actually in terms of practical. It's difficult to supply the power when we do not know when the user needs, anytime they need, right? So we need to have this battery in the middle, all right? So we have the battery in the middle to balance the grid. Power demand goes up, goes down, turn on, turn off, suddenly turn on the huge demand, huge electrical load, and then turn off. So it's very difficult to cater this demand. Alright? So for this, one of the application of battery is to balance the grid. Alright? So if we have the battery, alright, in terms of the supply, maybe the supply will be like this. If there is a sudden increase of supply, this will be supplied by the battery. Alright? This will be supplied by the battery to provide stability. That is one of the reasons of the drivers for the BESS adoption. Another factor is decarbonization, storing variable renewable energy, solar and wind, when production exceeds demand. So of course, when we have solar panel, solar farm, okay, large scale in fact, and this solar farm, the power output really depends on the weather. All right. So when the demand is low, but the solar generation is high, what we can do right now is to store this excess to the battery. For example, in UTHM, we have solar panel 6.9 megawatt peak, okay, and we have buildings, which is the electrical load, but we cannot store the energy. So especially during weekend, school break and so on, the consumption is very low, but the solar output is very high, right? Mean the generation is more than the consumption. Right now, without the battery, what happens is that the inverter will stop or will limit the production of output. It will only supply how much it's required, how much the building requires. So the inverter must do some kind of control to limit the output, even though it can produce more. Right. So if we have battery, this excess solar will be stored into the battery. So if we store excess solar to the battery, later on, next working day, we discharge the battery, use it to the building, then now we are using more energy coming from the solar. Alright? So this is why we can say decarbonization. We want to reduce our energy reliance from the grid. We want to, if we can get more energy from the solar, then much better. And in order to achieve that, we need to have battery. So next is grid stability, providing fast acting power to balance supply and demand instantly, preventing blackout. Alright, so this is another function of energy storage, battery energy storage. It can control the grid stability. Okay, we'll go into this later in a few more slides. And then the third one is energy shifting, capturing cheap off-peak power to discharge during expensive peak demand hours. This depends on the electricity tariff of your country. Like in Malaysia, the electricity price is expensive between 2 p.m. to 10 p.m. This is when demand is very high. So because the demand is high between 2 p.m. and 10 p.m., they put higher price for them. After 10 p.m. to the next day 2 p.m., that's cheap. So if we have energy storage, we can charge the battery during cheap price and discharge the battery for our use during peak. Right? So the core function of a battery is a well-designed gas can simultaneously perform multiple operations, maximizing the return on investment for asset owners. So again, we have seen that the battery is capable for various applications, various functions. So if you can design or you can try to plan your function for your battery to function more than one application, then it will be, you can maximize the return. So one of it is energy arbitrage, charging the battery when electricity prices are low, and discharge the grid or facility when prices are at the highest, like I said earlier. Second is frequency regulation, injecting or absorbing power in milliseconds to maintain the delicate 50 or 60 Hz. Depends on the frequency of your country, right? And also backup, providing seamless, uninterrupted power to critical facilities during catastrophic grid failure and blackout. These are actually just some of the functions. And depends on the situation as well. Maybe your battery, you cannot have all these three functions. Okay, because energy arbitrage, charge and discharge during expensive and low price, and this backup, maybe you can apply if the battery is connected to a building for local consumption, for the building consumption. But you cannot use this for frequency regulation. Frequency regulation is mostly for grid. You have bigger scale. This grid 500 kilovolts, so this is the size is much bigger, 500 megawatt hour, which is a utility scale. But of course, we have utility scale, you don't really bother about the energy arbitrage, the backup, right? Because the main concern is more on the how to control the grid stability, because the penalty if the grid is not stable is more than this energy arbitrage, this backup. Alright? Now let's go into the electrochemistry. What is LFP? What is NMC? Okay, so LFP is lithium iron phosphate. I think this is the most popular. Okay, lithium, for battery sometimes. Okay, lithium. Yeah, most of the applications are using lithium. So, and the second one is nickel, manganese, cobalt. This is why sometimes you hear the news cobalt mines. So these are all natural resource. Okay, which country that has these resources, they are very rich right now. We are using a lot. Okay, not just for the grid, for the power system, but also for electric vehicle as well. So that is another different topic. So we have LFP, we have NMC. So these are two dominant chemistries or two dominant batteries. So the right choice depends on the project requirement. Okay. So we have at the moment we have three attributes. One is the thermal stability. Second is energy density. How much is the energy that you can store in the battery? Let's say 1 kilogram of battery, how much energy it can store. If you don't bother about the weight, if you don't bother about the size, you can go for less energy density. And also the third one is life cycle. So thermal, basically safety. When we talk about thermal, it's all about safety. So LFP, in terms of the thermal stability, is high. Okay, safer chemistry with a higher thermal runaway onset temperature. The keyword here is less prone to catastrophic fires. Okay, less prone to catastrophic fires. On the other hand, NMC requires extremely robust thermal management system to prevent overheating events. So it's prone to overheating. So in terms of stability, it's not that good compared to LFP. So in terms of thermal, I think LFP wins, right? We choose LFP. This is why nowadays we are using a lot of lithium. But do not keep in your mind that we only have these two. Japanese researcher, they are also looking for, I think, like sometimes some kind of mineral, ionized, something like that. So there are a lot of chemical we can use for energy storage, right? Just focus on these two. Next is energy density. Okay, in terms of energy density, moderate, LFP moderate requires a large physical footprint and heavier containers for the same energy output. Right? Compared to NMC, nickel stores more energy in a smaller space. More energy in smaller space. Ideal for urban sites where real estate is highly constrained. So if you are concerned about the space, for example, like it depends on the space as well. For example, New York per square feet is very expensive, right? Compared to Raja, okay. So maybe there's a situation that you should go for nickel, manganese, cobalt because it can store more energy. But the problem is when you use NMC, nickel, manganese, cobalt, course, you can squeeze the size smaller to have higher energy density. So ideally for urban area, for building, for in the city area, but it is prone for overheating. You have another issue of fire. So maybe in this situation, you will consider that, all right, it's okay for you to put more safety, okay, because space is not an option. Okay, you pay more to have more protection for the thermal stability. So in this case, in terms of energy density, nickel, manganese, cobalt is better. And the third one is life cycle. So life cycle for lithium iron phosphate, okay, is longer, degrades slower over heavy charge or discharge cycle, okay, degrades. Of course, when you have battery, you charge, discharge, that is one life cycle, one cycle. Alright, so for lithium iron phosphate, you can charge and discharge between 6 to 8,000 cycles. Alright, and then for nickel, manganese, cobalt, the life cycle is shorter. Degradation occurs much faster under daily deep cycling routines. Deep cycling means that you discharge to very low capacity, charge up to 100%, discharge to 5%. So deep cycle. Okay. Then, if this is how you want to operate the battery using NMC, nickel, manganese, cobalt, it will give shorter life cycle. Right? So battery degradation, basic life cycle aging, wear and tear caused strictly by usage. Every full charge and discharge is considered one cycle. Okay, even your phone, okay, goes to 10%, 5%, charge back to 100%. That is one life cycle. Okay. Degradation speeds up if the battery is aggressively discharged, or deeply depleted. 100% depth of discharge will go into this term later. Okay, so meaning that aggressively discharge goes to 0%, charge back to 100%. So degradation speeds up if the battery. Even this laptop, it is recommended that you keep it charged. Right? Don't go to zero charge. Consider that one full cycle, but you keep using your battery or laptop like that, then it will speed up the degradation. Okay. If you have option to plug in, just plug in. Right? Have options. Of course, I'm sure my laptop can last for 3 hours, 4 hours, but it's better to, for the sake of prolong my battery laptop, I will keep it charged. It will not damage the battery.
Oh, keeping it charged will not damage battery?
Yeah.
I was thinking keeping it charged will damage.
Because nowadays it has auto stop if you fully charged, something like that. It has some kind of battery management system.
Yeah.
So just if you're using, just keep it charged. Okay, so you shouldn't leave it to be less than 100.
Actually, that is what I learned from this laptop. I'm not sure about different laptop. Maybe different laptop have different management system. You have to check. But last time I checked, just for this laptop, this is the unique of prolong is battery life cycle.
So leave it charged all the time. This is the first time.
Yep. Alright, so battery degradation, one is you consider or you count the life cycle. Okay, charge, discharge, that is one cycle. The second one is calendar aging, degradation that happens purely over time. So occurs even if the battery just sits unused in the warehouse. This also happens in the battery of our car. Okay, you leave the car without running, depends on the car. Usually my car, after 5 days, if not running, you have to ask someone else, please bring jumper cable, right? So even though you are not charging, discharging, but because of the degradation that happens purely over time, because it's chemical, it has some kind of chemical reaction, alright? So it highly accelerated by keeping the battery at 100% state of charge or exposing to high ambient temperatures. This, I have to say something, high ambient temperatures. So in Malaysia, if the temperature is high, in terms of the battery efficiency, not good. It must operate at certain temperature, ideal temperature. So if the temperature is high, we have to have some cooling system. But maybe after this you go to Canada, you work in Canada, where the temperature is very cold, you will have issue with colder temperature. Battery also doesn't work well at very cold temperature. Alright? So I think similar to human, 24, 25 is nice, but 36, 37, not good for us. But negative 10, negative 5 also not good for us. So battery is also chemical like us, organic basically. It must have some certain sweet temperature, sweet point that can operate at best level. Alright, next is balance of plant. So balance of plant, what is this? It's physical hierarchy. So utility scale. Okay, utility scale. This is where the battery we use power system. It's highly modular, meaning that you can scale up, you can add more. If in the initial planning you have a large land that you have accommodated for this project, maybe you will install 10 units first. Okay, in future, seems like your system requires more, you can add more. It's modular. Usually utility scale is modular. So you can just increase the size. Alright, so in terms of the hierarchy, first is basic, is battery cell. That is the, usually I suppose in any manufacturer they are still using the same size, same battery. Okay, and then so this is the foundational unit, cylindrical, very common. And then once you have all these battery cells connected in series or parallel, depends on the design, it will form modules. Okay, we got 3 modules. Alright. What we have in UTM, the modules is like this, about this size. It's a module, one module. Right? Not like this is vertical. It depends on the manufacturer. But certain amount of this battery cell, you connect it together, it forms a one module, and you have multiple modules connected together. It can be vertically, okay, connected in series. It will become string or rack. One rack. Okay. So one rack you put into one container. You can have 3 racks in one container or 6 racks in one container. Or what we have in UTHM, we have 2 containers, DC container. Okay, we have 2 of these. And if you visit the PES at UTHM, you will see it has 6 doors or 6 panels. Each of the door goes to one rack. Open one door, you see one rack. Open one door, you see one rack.
So each one of the containers consists of the small battery cell?
Yes. So this one huge container, this is one rack. Okay, it has multiple modules. So you take one module, inside the modules you can find each of these cells.
Okay, the same small one that we use in the remote control, or
The remote, the TV remote is AA or AAA. This one is different. But it's about the same size, slightly bigger actually. I don't have the example.
The container has means of ventilation.
Yes. We'll go into that later on the safety of the container, right? When we have issue with thermal stability and so on. So what is the requirement for the container to cater all this problem, thermal stability and so on. But the physical hierarchy of the battery is this. And then of course you can replace if there's a problem with the sub module, you can replace the module. I don't think they will replace the cell. Of course, we can go into that level to find out which cell has problem, but I think they will just replace the whole module.
Not to waste that.
Maybe in terms of the effort, the cost to go into that, each one is more expensive. You know, you have to design all this airtight as well. So, and then you have the battery. Then we have the battery itself is not enough. Okay, we have PCS, power conversion system. This is where I think you're expert. This is where your background goes into this PCS, convert AC to DC, DC to AC, both ways, because battery is charging and discharging. All right, so both ways. So this is what we call gateway to the grid. Battery to the grid must have PCS, power conversion system. Maybe it depends on the manufacturer. Sometimes they change this term. They use different term. Alright. So batteries naturally output direct current, of course, plus minus, positive, negative, right? But the electric grid operates on AC, alternating current. So PCS bridges this to AC and DC, and it must be bi-directional, charging and discharging. So conversion converts AC to DC to charge the battery. When you charge the battery, AC from the grid converts to DC, and then DC to AC when you discharge the battery to supply energy to the grid. Also, function of PCS for grid synchronization, right? PCS must be able to match the grid frequency. Frequency 50 Hertz. Your PCS, this is DC, must be able to simulate or generate AC at 50 Hertz as well for safe interconnection. Also, to synchronize, even though it's generate 50 Hertz, must be able to synchronize as well, right? Right now, this is the 50 Hertz signal from the grid. And your PCS, of course, can generate 50 Hertz as well. Alright, this is also 50 Hertz. 0.02 second, right? 50 Hertz. This is also 0.02 second, 50 Hertz. But it doesn't synchronize. It must be synchronized as well. It must be at the same point. Synchronization. 50 Hertz is just 50 Hertz is not enough. You must be able to synchronize, right? Then power quality, smooth out voltage spikes and control the RAM rate of the power dispatch. Okay, control the power dispatch. How much you, for example, this our phone charger. Sometimes you see in our phone charger 20 watt, 100 watt. Sometimes nowadays can go 200 watt. So PCS must be able to control how much power it wants to output at a time, right? So and then PCS, once it's converted to AC, we need the next one to step up the transformer. So if the output of the PCS is 480 volt or 600 volt, I think for UTHM is 600 volt, 600 volt AC. Then next the transformer will step up to match the voltage of the grid. So in our case, in THM, we have transformer that step up from 600 to 11 kilovolt. Okay, because you cannot connect, straight away make the connection, not the same voltage. But if your battery wants to connect to the building, using the building, for example, even this building is 415, 415 volt, then your PCS connect transformer goes to 415. And then switch gear. This is switch gear is where you connect transformer to the switch gear. Switch gear connects to the load. All the buildings or the load. Switch gear is basically a switch to switch on, switch off. You switch off so you can do all the maintenance for the battery, maintenance on the transformer. Once you do all the maintenance, you switch on. Alright? Because you don't have switch on and off at the transformers. Right? Okay. Alright, so we arrived, we have arrived to this learning activity. Now it's your turn to do some discussion. Okay, please open the handover I've given you. So you can discuss, alright, discuss. Trace the flow of power from the electrochemical energy source to the utility grid. Order and connect the following components to create complete. Okay, we have all these battery cells and so on, as I have go through in the earlier slide. Just please discuss which should go first, second, third, and fifth. This may be not in the correct order. Alright. Okay. I can give you 5 minutes to discuss.
It's like it's been arranged way.
Uh-huh.
It's like it's been arranged sequentially because you have battery cells and next goes to module, then power conversion, then we're going to have the step of transformer. Then
Yeah.
so it's sequentially arranged. Sequentially arranged.
Actually, I want to shuffle the order, but let's just keep like this. See if you understand it.
It's
Except for those should be like switch gear. Switch gear after the transformer.
yeah.
Then you can go to the grid.
Utility.
I think there's but we can see the small pieces. Then what to the sunlight. Then
The one direction here is the battery.
then it's the next one what to
Which one should go first in terms of the structure? For the battery,
these are the
first, second, third.
and then the next one.
First, we have to get the
So
Yeah, the picture here. Nak pilih. Kau tak dapat. Hah? Macam ni.
Pemasangan.
Nah.
Is in the correct sequence.
Ah.
Kan?
Yeah, yeah,
Yeah, just draw.
Pagare portare il telefono sembra che è una cosa di PCS. Non genere di solo. Vai, quindi non sapere però il
So we need step up with the step up, and well, we have to step up. Maka itu bisa maka
Ustaz berapa ni? Tom?
Berapa?
Okay, maybe you can just explain your answer. Tell us your answer for the first activity.
The first activity is being arranged just as the switch gate not way, because it's arranged sequentially.
Okay, so basically the arrangement is correct.
Yeah, the
First one, okay.
Yeah, that's correct.
All right. Okay, I think I just want to make it like a trick question. I want to shuffle the order, but I think like maybe I just give this a trick question. Who knows? Maybe someone will change the. So the order is like that: battery cells, and then you have multiple battery cells. You have modules, and then you connect all these modules. Then you have racks. You have multiple racks into one container, and then connect container to the PCS. After that goes to the transformer, step up or step down, depends on the situation, depends on your case. And then you can connect to the utility grid or your building. Alright, so okay, let's continue. We are about to finish module 1. So let's do a quick review or recap on the learning outcome. So initially, our module 1 aims to for you to understand on the core function of BESS, right? So I think we all now understand. For example, Mujahid, one example of BESS. What we can use for BESS? Function of BESS. If you can recall, energy storage.
you can use it for solar.
Uh-huh.
How you gonna for solar when
Uh-huh.
its demand is high?
Yes. One of it is to like earlier decarbonization,
Yes.
right? We have excess of energy that we cannot use as a moment.
Storage.
Right, correct. That is one core function of BS. One of it. Another is buy cheap, use charge during cheap, discharge during expensive, right? And then yep. So and then again, you want to grid synchronization as well, right? To support the grid, right? And then okay. So number 2, can you compare attributes between LFP and NCM? Okay, lithium iron phosphate, nickel, cobalt, manganese, NMC, nickel, manganese, cobalt. All right. 3 attributes, which is density, thermal stability,
The last one is life cycle.
life cycle. So in terms of thermal stability, which one is the best? Lithium is the best. Thermal stability. In terms of energy density, nickel, right? Nickel can store more energy in a smaller space. Life cycle, LFP is much better, right? All right. So and then finally, physical hierarchy of the battery. I think we have done in the one of the exercise. Okay, the hierarchy from cell and so on. Cell, modules, rack, containers. What else? PCS next to switch gear and then. Right. Okay. Now to the toilet. If you want to go to toilet, it's okay. I think toilet is that direction. Okay, so let's continue with the second module. Second module is on battery management and safety control. Right. So now we have establish our understanding on the BES architecture. Now we have connect our battery to the grid. How we want to manage the battery, and then how to control what we can do for the safety of the battery. Not just for the safety of the safety of ourselves as well if we visit the site. So in the second module, our learning outcomes is we want to understand what is SOC, what is SOH. Okay, that is the first one. Second is understand the stages of thermal failure. Okay, we have to understand the stage of thermal failure so that we can plan how to mitigate this problem. Right? So then, once we understand the stages of thermal failure, the third outcome is how to mitigate this failure. What is our strategy to mitigate this failure? Okay? Because after millions of ringgit you invest on the battery, all right, if failure happens, if there's a fire, hopefully it's contained to only one container. Right? Right, first let's understand the battery brain. This is the brain of the battery, which is BMS. Sometimes we call it EMS, Energy Management System. Battery Management System. Anyway, it's basically a computer that controls the battery. Right? So utility scale BESS relies on hierarchical structure to safely govern thousands of individual cells. We have thousands of individual cells in just one container. So imagine for utility scale, we have a lot of containers, hundreds of containers. So to safely govern these thousands of cells simultaneously, because you cannot, okay, please do not expect that you drain the battery or discharge the battery, the first cell, and then once this first cell finish, you discharge the second cell, discharge the third cell. It's not like that. It's not like this water you drink, finish, you take another bottle. It's not like that. BMS operates, you have a lot of water, drink all this at the same time. Okay? So because if all cells drain at the same time, then in terms of the life cycle will be the same. Okay, we want to make sure that life cycle is the same for all cells. So because of that, we discharge and charge the cell all at the same time. Right? So control thousands of individual cells simultaneously without overloading a single processor in your computer. So tier 1 cell level directly monitors individual cell voltages and localized temperature. It executes direct cell balancing, right? Direct cell balancing and serve as immediate first line of defense against overcharging at the granular level, right? So now basically what you need to understand here is we have battery management system. Okay, this battery management system, when we call system, you imagine like some kind of computer brain that controls everything. We have brain or computer that control the cell level. Each rack. Sorry, each modules. Right? Each modules. And then each module has thousands of cells. So we have system that look at this level, this cell level. One module, we have thousands of cells, and each cell's level. We can actually have that. Okay, we can see that in our UTHM system. Okay. But that is you have to go to the DC container, open the side door, and then you can access the system. Right? But when you in operation, that is not your concern. It's not our concern to understand this. What's the status of this cell? What is the status of system? Because thousands of cells, Alright, so this cell level, the BMS, it will monitor, execute direct cell balancing, okay, charge, discharge all at the same time, and also try to avoid overcharging, right? And then we have another system that look at rack level, okay? So it's kind of controls multiple modules. We have these modules to look at the cell. This is a rack level that looks at each module in one rack. We have multiple modules, right? So responsible for calculating the rack level matrix, okay, and then check on the voltage level, power level for each of the rack, each of the modules. So BMS to control on the rack level. Okay, it's quite complicated because in the end we want to charge and discharge all cell at the same level, right? And then master controller, it aggregates data from all racks, communicate with the external PCS and site energy management system. This is where it connects to our load, how much the load is demand right now. Then the DMS will, the system level will discharge, communicate with PCS so that the battery discharge. That is the 3-tier BMS architecture, right? In cell level, 3.7 volt. 1000 of this cell level, you have one module, right? So this is the cell level of the BMS. You have computer, right? I think later on, maybe in another day, we can have a visit, right?
Wow, what?
Visit of our battery project.
Oh,
But right now, if you want to open this panel, it will shut down the system. Right now, it's operating. It's now discharging. Started operation this month. So we have to like find a suitable time, arrange a time so that we can open and see actually the system, the module or the controller, module, the controller that control each rack, and you have all these racks together. We have one module, master BMS, that control all this. Because in the end, this master BMS must control each cell. Okay. I think like if you want to imagine, you have house, you have family members, one leader, and then you have one street, multiple houses, you have one leader, and then all this village have a lot of house, a lot of people, and everyone needs to stay in order, something like that, to control everything. Okay, so next is SOC, SOH. State of charge, state of health. Right? Two different things. So state of charge, you can imagine like a fuel gauge. Okay, how much you go to the petrol station, you fill in 10 liters of petrol, something like that. That is the amount of energy in the usable energy capacity. Okay? Usable energy capacity in terms of percentage. Right. Calculation use counting, tracking, entering, leaving the battery combined with open circuit voltage. Okay, go to this later on. Basically, SOC tells the operator or us exactly how much energy is available. Okay, how much energy is available. State of health is the odometer or wear tracker, for example, function compares the battery current maximum capacity to its original factory capacity. From the factory, it says it's 5 megawatt hour or 10 megawatt hour. That is the state of health when we purchase it from the factory, right? But after 5 years, after 10 years, is it still the same state of health, right? Evaluated through internal resistance tracking, capacity factor, right? That's the detail of it. Let's look at the picture, to make us more clear. So, state of charge. Okay, this is the battery, the capacity. Right now, what is the state of charge? Right now, how much is the energy it has that can deliver to us? And then the difference is the only depth of discharge, how much it has discharge. Depth of discharge. Okay, so state of charge, how much will the difference? So here, for example, let's say SOC is about 90%, right? 90%, and then the power is 0. Now we want to use the energy from the battery, so it's discharging. So the PCS turn on, deliver power 0.5, depends on the rating. Let's say if the rating is 5 megawatt, then 0.5 is 2.5 megawatt, half of the rated power basically. Discharge the energy to the grid, then the energy from the battery slowly drains. Okay, enough, stop, to 0. This is state of charge, right? And then the price of electricity is cheap now. Okay, we charge the battery, so it's negative 0.5 because we're charging the battery. Charging the battery at 0.5 of the rated power. Now the state of charge is increasing. Stop charging, then state of charge. Okay, I think it's straightforward. Okay, I think state of charge is very straightforward. The difference is state of health. Right? Like I said, when we first purchase the battery, the state of health is 100%. Our battery at UTHM is 10 megawatt hour. So supposedly is 10 megawatt hour. If the state of charge is 100%. Of course, after we purchase, now I think almost 1 year, okay, we have some degradation. We have learned two degradation previously. One degradation because of life cycle, charge, discharge. One degradation because of time, calendar time. So after that, it has some degradation. So the state of charge is no longer 100%. Okay, let's say after 5 years, it can no longer store 10 megawatt hour. It can only store like 9 megawatt hour. So state of charge is 80%, for example. But with that amount, the state of health, right? State of charge, you can still go to 100%. But it's no longer state of charge is no longer 100%. That's the difference. SOH is referred to the initial health of the battery, right? In fact, when you want to purchase electric vehicle, nowadays the electric vehicle they put a warranty on the battery. I think Perodua, for example, they put warranty on SOH. When you want to put warranty, you refer to SOH, state of health. So if I'm not mistaken, like after 5 or 7 years, if the state of health of the battery goes below 70%, something like that, you can replace with a new one. Because the battery is not good. It can degrade very fast over years, over the time.
But this state of health, like you said, once the battery is charging, the state of health is being maintained. Does it also apply to our phones?
To which one? Yeah.
Does it also apply to our phone?
Yeah.
Because you say your system, you always keep it on charge. and the state of health will be maintained.
Uh-huh.
Does it also apply to our phone?
Font, I think goes back to the previous theory on degradation. Degradation because of charge, discharge, charge, discharge. A lot of that doing that, it will degrade the battery, and then over the year it will degrade. Not because of charge, discharge, but even not using it over the years, the state of health reduce. Uh-huh.
And this cup you've shown before, that when it is charging, when it is discharged, it goes down. That's the cup. When it is discharging, it goes down. What of when it is charging? Should it be going up or should maintain? Because you say while charging, it maintain. That is from 1.5 to 2.5. What happens there? Yeah.
This one.
Yeah. What's happening?
No, this is the battery is not operating.
Oh, it's not operating.
CCS is 0 watt.
Okay, so it's not charging.
It's not using. It's idle.
It's idle.
It's idle. So that's why it's still maintain the state of charge.
Okay.
Uh-huh.
So they're going up there. It's charging.
Going up because now is charging the battery at 0.5 or the rated power.
Understand.
Uh-huh. So the difference between SOC, SOH is SOH you use it for mainly for warranty. When you purchase battery, I want to have this battery within 10 years. Its state of health is still above 80%. Because anyone can claim, okay, my battery is 10 megawatt hour capacity, very cheap, you can buy this one. But who knows, after 5 years, it degrades very fast because the quality of the chemistry, the raw material and so on. So SOH is something you should consider when you want to look at the quality, right? So SOC is still always 100%. After 5 years, you can also 100%, but in terms of the megawatt megawatt hour is different. Alright, so just quickly on the picture, after many cycles, of course we have a lot of cycle use, it will degrade the battery. So the state of health, okay, the capacity initially, the battery in terms of the capacity is 1.7, 1.8 for example. And after many cycles, many times of using it, charge, discharge, state of health will go down. You cannot store the energy as much as initially when you purchase it, right? All right. So SOH. Again, I think we have covered this full performance end of life threshold. So if you set 80%, then maybe you can replace a new one. But again, interesting about SOH. If we talk about electric vehicle, this battery, for electric vehicle, let's say when you purchase it with your full charge, you can go 500 kilometers, right? But maybe after 5 years, full charge, you cannot go 500 kilometers. You can only go 350 kilometers because of the degradation, right? So in terms of the electric vehicle, even though the state of health is maybe 80%, which is for us, you cannot reach 500 kilometers, not good. For us, it's not good. But you can still use that battery for different application. For example, you take the battery and use it for street light. For street light. Okay, that is another application. Because for street light, it doesn't matter if you in terms of the size. If you cannot.
Just for lighting.
For lighting, if cannot,
so
it
there's
cannot.
no rotation, no motion.
In terms of light, for example, if you use the battery, it can only light for 6 hours. You put more battery, it can last 18 hours. It's not the problem of about weight, because for car, weight is very concern. It's a big concern, the weight of the car.
There is weight ratio
Uh-huh.
going like retardation.
So for depends on the situation, maybe for electric vehicle, 80% instead of health. Below than that, not good because our car is not reliable enough, but can still use for different applications. So SOH, we have to look at. So it's not a single rule, 80% for all application, depends on the application. Again, methods in predictive maintenance, check on the performance, guarantees, safety as well, is related as well. We go into activity after this. And also financial planning. Okay. Where you have to state, okay, now we see that after 5 years this SOH dropped down to 85%. I think we have to start putting more battery, right? Right, capacity loss, check on the capacity loss, internal resistance. This is how we measure the state of health. Voltage current profile. Of course, all this is actually in battery management system. Okay, all these are in battery management system. You can get this data, but you need to know SOH for then the requirement. Okay, probably you have to upsize or oversize it upfront. Okay, you require 10 megawatt hour, but maybe because of degradation and so on, okay, let's just request over capacity, slightly upsize or oversizing. Plan augmentation, hybrid strategy, cost optimization, AI-driven BMS. So all these you need to consider. Alright, AI-driven BMS, for example, like you need to consider BMS that can control the battery, even though the SOH is going down. At 80% is still able to manage how much power you need and so on. Alright. Okay, quickly on this, manufacturing variance cause individual cell voltage to drift apart over time. BMS must realign them to maintain maximum pack capacity. Passive balancing, active balancing. This is actually function in BMS. In BMS, you need to ask your manufacturer, does it have passive balancing? Does the BMS has active balancing? This is also important in when you want to purchase BSS. Okay, passive balancing uses bleeding resist to burn off excess charge from high voltage cells as heat. It's simpler, cheaper, and standard in most utility storage. It's the simple one. Active balancing uses capacity to shuttle charge from high voltage cells directly into low voltage cells. It's highly efficient and generates less heat but adds significant hardware. Basically, going back to the first one of the slides that I talked about, all cells must discharge and discharge at the same time, right? All cells must discharge and discharge and at the same time. We need to have same state of health of the battery. We cannot discharge the battery by cell all at the same time, right? So in order to have that, of course you cannot have perfect everything, every cell 80%, 80%, 80%. In real life, some cells will go to 80%, some cells will go to 81%, some cells will go to 85%. So if you go for active balancing, it has its own, okay, I'm not going into detail about this, right? You know more than me, I suppose.
No.
It has some kind of technology that try to manage high voltage cells, the cell that has high voltage, high energy, okay, store more energy, okay, it will go discharge go to low voltage cell. Alright? Balancing. Try to balance the level of state of charge of each battery. Okay, passive balancing, active balancing. Alright. Next is safety and thermal management, triggers of thermal runway. Very important. Okay, I intentionally put this in this order. MITE, might. So easier for you to remember, might. Mechanical abuse, internal defect, thermal abuse, electrical abuse. These are all can trigger thermal runaway. Battery becomes overheat, it can start burn, and the whole container burns. Okay, because of mechanical abuse. Crash, puncture, impact, okay, it can disturb the integrity of the structure of the battery. Of course, we don't want that. Of course, once we install the battery, I don't think we're going to move it anywhere. It's very heavy, like 14,000 kilogram each DC container. So, except for during transportation. During transportation, yeah, this could happen. Okay, next is internal defect. Microscopic manufacturing flaws that slowly pierce the separator over months of years of cycling. So this is internal defects during manufacturing. All right. Third is thermal abuse, operating outside safe ambient temperature windows, causing internal plastic separator membrane to melt. This is one of the examples, but basically, if you try to push the battery to operate at outside safe ambient temperature, you can you abuse basically, right? And then finally, electrical abuse, overcharging beyond safe voltage limit, or deep over discharging, which causes copper dissolution and subsequent burnout. So again, going back to your question, some battery without the proper BMS, you can overcharge. But again, for this computer, all right.
What of my computer also has?
It's how will one know that his computers that's safe?
I'm not sure how to answer that. Maybe I have to check on the manufacturer.
Does it have this?
We have to go into the manufacturer, maybe like the manual or something like that.
Okay.
To check on the manual.
I'll check on the manual.
Or nowadays you can just ask AI, put in the model, does it have battery management system? It's easier for me to just keep charging. But I understand your concern. It's actually a problem that depends on the system. If it has some kind of safety protection to avoid overcharging, then it should not be a problem.
We'll check the manual.
Mechanical, internal, MITE, mechanical, internal, thermal and electrical. Okay. So stages of thermal failure. First is thermal runaway progresses through predictable stages. Early detection is the key to prevent catastrophic fire. So we have to understand the stage. First is incubation of casing as temperature rise internally. So this is the first stage. Temperature rise internally. Liquid electrolyte vaporize and burns highly flammable gas. Okay. So, or we call it volatile organic compound, VOC. So, the first stage is it will produce gas. So, if we have sensors, we can detect this before the fire. This is before fire. It will start by releasing gas. Okay. So, we need to have gas sensor inside the container, right? So, first module we learn about the structure of the battery. Now we need to understand about the safety. So the battery will release gas. In order to mitigate that problem, we have to install sensor to detect this gas. Right? Second, let's say the cell structure fails, bursts, and ignites. So then this will give temperature, high temperature. Sometimes it goes very extreme, 400 to 800 Celsius. Alright, and then it continued to cascade thermal failure, intense uncontrollable heat transfer direct to adjacent cell or the adjacent modules. So triggers chain reaction of sequential cell ignition. Okay, so this is the stage, right? So we have chemical. First stage is it will release gas, right? Release gas, and then you have fire combustible, and then it will continue to the next module, to the next cell. So let's.
New tonight at 11, they can catch fire, releasing deadly fumes. These battery energy storage facilities help support the power grid, but there is risk involved. Now, one could be approved in a residential neighborhood. CDSA's Brian White investigates.
3 fires in a year, one in Valley Center, another in Otay Mesa, and more recently in Escondido at this SDGD facility where one of 24 battery containers caught fire. It's called thermal runaway, a chemical reaction when lithium-ion batteries overheat.
Once it starts, there's no way to stop it. Really, the fire that's happening inside the battery has to run its course. So that chemical reaction really can't be stopped.
These fires can take days or even weeks to burn out. The one in Escondido lasting 13 hours. The one in Otay, 17 days.
The big concern for us is what's toxic and how far is that going?
San Diego Fire Rescue Battalion Chief Rob Rossetti coordinates responses to these types of fires all over the county. He says they use atmospheric monitoring to check for toxic gases like hydrogen fluoride and hydrogen cyanide, which can be deadly.
You're going to smell that carbon, that soot material that's being burned off from the fire. The question is the toxicity being traveled with it? And that's what we do. We go into the smoke, we take readings from the smoke.
And those readings determine how far out people should evacuate. He says weather plays a huge role in how or where the plume will spread. Temperature, wind, and humidity are factors.
From our experience, the soot that floats in the air floats way further than any of the toxic gases that's coming from the batteries. So realistically, you're going to smell smoke much further than the toxic particles can travel.
But that does little to calm the nerves of people living in the Eden Valley neighborhood near Escondido, where the developer AES is looking to build a 320 megawatt energy storage plant, the third largest in California.
It's ridiculous to put this toxic bomb in this valley. If you look around the valley, it's a small valley. It's surrounded by homes.
Not only that, the 22-acre site would be 1,600 feet upwind from Palomar Hospital.
The risks of battery projects are very real.
Joe Rowley lives in Escondido. He's a former Sempra Gas and Power executive. He works with the Stop Seguro group, pushing back against the project.
The Seguro project is the poster child for where not to put a large-scale battery project. It's too close to residences, it's too close to a hospital, it's too big.
Battery energy storage systems, or BESS facilities, are typically located in industrial zones. AES chose this site here in part because of its proximity to SDGD's Escondido substation, where they would tie into the power grid.
I think it's something that instills fear in all of the residents here. Our biggest concern is the fact that these lithium-ion batteries light on fire. And once they light on fire, they're emitting toxic gases.
The proposed Seguro site is actually in unincorporated San Diego County, so the Board of Supervisors will make the decision.
It's vital that we protect the health and safety of residents, and that's non-negotiable.
In September, the county opted not to pass a moratorium, but they did hire a consultant, Jensen Hughes, to make recommendations.
I think you get the idea. When it happens, then hopefully we don't want that to happen. Imagine how to respond to all these questions from the community, everything, because our intention to have this battery energy storage system is to provide reliable power supply to the consumer, to the community.
So until now, when it's catch fire, they cannot control it. So there's no go back until all
we can control. Sometimes 17 days.
17, depends on.
No, well, after all the various drains, right? This 17 days period, after all of them already burned.
I think one of it. depends on 17 days. That is different case. I think for that one is hours. Take hours. That one.
Depending on how large it is.
Uh-huh.
And also, you know, it burns the chemical reaction of coal. So that's the issue.
So it can be stopped.
Yeah. So if it move to the different container, that's
but the ones we have in most of the houses, you find out it's a single module. Does it have such risks?
Still have risk because it happens because the thermal runway start from
Because
each cell.
the reason why I'm asking you, back in my country, where some areas you find that because electricity power is there's a lot of outage.
Okay.
So people use this battery. So you find out that one just a single module in his house. Like some even keep it inside their sitting room. Like
Yes.
this. Yeah. So I don't know, does it have also risk factor?
I think in terms of the
You find out somebody will have like 12 volts. 12 volts.
Okay.
Like 12
in the
volts,
car.
in that car 45 amps.
Okay.
Or 70 amps, you find, or 200 amps, there 200 amps battery. So you find a 200 amps battery inside a sitting room, used for solar. Maybe it has a 2 or 3 panels. That risk also?
Well, if you go into each cell, in terms of the cell, it has a risk. It's called thermal runaway. Okay. So now the thing is how to avoid this thermal runaway. Again, MITE, right? Mechanical, right? One of it is thermal, right? Of course, the internal, the mechanical, that is electrical, that is something else. But to control this thermal abuse is again going back to the battery management system. How you can control so that if the temperature goes high, cooling system goes into the system, start operating cooling system, not to overcharge and so on. So BMS, so very important, right? To control again active balancing as well, right? We don't want certain cells high voltage compared to other cells, all right?
New tonight.
All right, so before finish module number 2, fire mitigation strategies. Again, first is because of the gas. All right, start with the gas. So modern BIS enclosure. Okay, the container employ multi-layered suppression system to safely manage or extinguish events complying with. We have standards to follow. So make sure you follow when you want to purchase the battery. Check out the standard. One of it is clean agent gas system like NOVAC deployed early to flood the enclosure. So it's like they suppress flames by removing heat rapidly. Okay, it actually in the container it actually gives some gas to suppress the flame. Right? Aerosol system discharge findings of solid particle and gas that chemically interrupt the chain reaction. And then water, the final line of defense for first responder uses massive volumes of water. This is what you see in the video. Okay, when this fails, when these two fails, and it cannot contain the fire, then you have called the fire department, use water, right? I'm not sure if they have a new technology like they use in electric vehicle. I think in electric vehicle they use fire blanket. Because I think EV, right, macam EV, fire blanket, because EV is small enough to have a blanket and cover, completely stop the oxygen and so on, right? But for container it's quite huge, but I think 17 days they can find blanket quickly. 17 days is not stopping. Right? Yeah. Okay. So learning activities, let's do quickly go to this activity. The second activity, we have a scenario, right? Number 2 shows rapid state of health degradation over month reach 75% state of health. Then, even though the state of charge is 95%, meaning that is charged as 95%, state of health is dropped 75%. Then suddenly cell number 14, you can see this from the BMS, unexpectedly reach 85% and trigger alarm, volatile organic compound gas alarm. So discuss 5 minutes, 10 minutes. So first, how do the prior SOH degradation and SOC really help us diagnose? From the SOH value, from the SOC value, how does these two values help us to diagnose the root cause of this? And then, based on the 85 reading, I think this is it. I forgot. Oh yeah, 85 degree reading, with the temperature and the alarm, what stage of thermal failure is in the cell? And then, how to mitigate. Okay, just maybe 5 minutes. Dia belum siap lagi yang dashboard. Dia akan buat.
Kita boleh akses.
Sepatutnya boleh. Dia sebab dia ada komputer, tinggal lagi akses remote. Belum siap sepenuhnya lagi lah. Itu dia ada juga.
Kami selalu dia tunjuk kanannya.
Itu tapi
pakai laptop dia je lah. Sambung USB lah.
Itu yang dekat panel kan?
Oh, tak dengan laptop.
Itu laptop tu yang dia memang bila lipat terus masuk dalam tu server tu.
Macam apa tu?
Yang built-in,
HMI lah.
Dia memang built-in.
Macam apa? Sekadar lah.
Yes. Dia memang built-in dalam tu, tarik. Tapi dia nanti akan buat satu dashboard yang kita boleh monitor dan control
secara remote lah.
Sebab susah kita macam
kena pergi site. Sekarang ni masih pakai sekadar je lah.
Dah sedia dah. Okay, check sorry. This is number one. This is for question. This is actually we have 3 questions. This is of question number 1. This is question number 2. Alright, so this is question number 1, 2, 3. Then this is question number 1, 2, and 2. It's already there. Just to speed up the process.
Answer the questions.
So ada apa-apa safety equipment yang diperlukan?
Ada.
Di dalam.
Dalam kontainer tu kita boleh nampak dia punya gas sensor, smoke sensor, and heat sensor, heat detector.
So heatnya dalam building atau
dalam
sel? Dalam kontainer.
Dalam kontainer tu dia buka panel tu kita boleh nampak kat. Dia ada kontainer sini kan, kontainer sini buka. Dia ada gas, smoke and heat. Macam gas, smoke, heat. Gas, smoke, macam tu lah. Ada satu tu ada 2. Alright. Alright, okay, I think let's just continue later on the okay, never mind. So module 2 review, let's just quickly recap on module 2. The learning outcome for module 2. First is what is SOC, what is SOH. I think we have understand state of charge, state of health, right? very important to check the quality, the performance of the battery. And then number two is what is the stages of thermal failure, right? We have stages of thermal failure. First is start from the cell release the gas, all right? Start releasing the gas, and then if you continue, then you have fire. Start from the cell, and then it will continue, right? Get much bigger. So initially you must have gas detector, right? And then what is the verification strategy due to fire? So again, you have um, uh, start with the gas detector. You have the smoke detector. You have the heat detector, and then
Water.
last is water. Last is water, right? Right. That is the worst case scenario. Hopefully, we will not encounter that, right? Okay, so we have about 1 hour left. We'll just quickly finish module 3, module 4, and then we recap for the whole session, for the whole training session. Module 3, grid integration and application. So we have the battery in module 1, the structure. We understand the battery management system, the safety, what we need to have to for the safety of the battery operation, state of charge, state of health, so on. Now we want to integrate that battery to the grid and start use this battery. So we'll learn two keywords here, FTM, BTM. Two keywords here, FTM, BTM. So these are the two learning outcomes for this module. Okay, by the end of this module, we want to understand the FTM, front of the meter, behind the meter, FTM, BTM, these two. So understanding the front of the meter. So this is the meter. Okay, front of the meter, behind the meter. So your battery is for which application? Is it for front of the meter or for the behind of the meter? So front of the meter, you have transformer, point of common connection. Basically, these are the grid level, utility level. If your battery is for this function, then we call it front of the meter. For UTHM battery, we connect it to the building, so we call it behind the meter. Okay, behind the meter. Okay, for various application, which is behind the meter. But it's still possible for the battery that we use for behind the meter application can also serve this part as well. It's not impossible. It's possible if the size is large enough to support front of the meter. Why not, right? So
let me understand this one. Front of the meter, behind the meter. Does it has to do with the type of output? Behind the meter, maybe DC, front of the meter, AC? Or
no, it's mostly application. The application. So here, front of the meter is utility scale system directly connected to the grid transmission or distribution of the grid, but not at the load. Okay, usually this is owned by utility or IPP. Even battery nowadays is not just for the transmission or distribution, even for the generation as well. We can use battery for generation as well. Previously we have visitor from Kenya power generation company, something like that. So their interest is to use battery for their hydro power plant. All right. So a lot of application for battery. So for front of meter, primarily in wholesale energy markets. Basically, the goal is for grid stability, frequency support, large scale renewable asset integration, right? Because the penalty of not having a stable power supply is more than the penalty of saving from peak price, right? That's the concern. This front of the meter. Or behind on the meter, usually for commercial, industrial, even residential houses, right? So this is behind the meter of the application of the battery. So asset is owned by the facility owner, right? Maybe lease. So it basically operates to serve the local facility, the infrastructure of the local. So bill reduction, the goal is bill reduction, maybe backup power for the building and corporate sustainability, and even like for data center, they can use as backup as well. Right? Demand management, this is grid scale front of meter, maybe for the grid infrastructure to support the renewable power. Or behind the meter, it localized energy storage, access from solar, maybe energy conservation and management by during heat use during expensive, right? So on. So that's the difference between the two. Front of the meter, behind the meter. Now, fast frequency response. Okay, the electrical grid must constantly balance electricity supply and demand to maintain a frequency at 50 or 60. Failure to comply this will lead to collapse of grid. You cannot control the frequency, the whole grid collapse. So this is for battery application front of the meter to control the grid. Okay, to control the frequency of the grid. So battery with the PCS, the inverter and so on, can inject, discharge and absorb or charge massive amount of power in milliseconds to counteract frequency deviation. Frequency deviation, alright, any deviation of the frequency in the power system, battery through inverter can react to control the frequency. That is for grid, for the transmission. For the power generation, okay, synthetic ignition. As heavy speeding fossil fuel turbines are retired, the grid loses its natural physical inertia. Battery steps in to provide a fast-acting buffer that prevents blackout. Okay, I'll have picture or graph to explain on this. So this is called grid forming battery. Based on grid can set voltage and frequency basically to support, okay, to support the grid. Okay. So we have two things: grid forming BESS or battery, grid following BESS. So these are some of the application of battery, right? To support grid following is grid feeding. So it support energy to the grid. Grid forming is to set the voltage and frequency to control the stability of the power system. Right. So continue. FTM, front of the meter, spinning reserve. Okay, three applications for front of the meter. Function of battery, spinning reserve, act as immediate standby power. If traditional power plant tripped offline unexpectedly, then battery discharge to cover the shortfall. Second is voltage support. Okay, FTM, function of battery to support the voltage, inject, absorb reactive power to maintain or stable localized grid voltage. Okay. Third one is smoothing the volatile output from the solar and wind farm, especially for large scale solar farm. Suddenly there's a huge cloud cover because large scale solar farm is connected to the grid. For UTHM solar, directly connected to the building. So large scale solar farm is directly connected to the grid. If there's a huge cloud cover the solar farm, then it will disturb the disturb the power supply of the system, the stability of the grid. Alright, let's go one by one quickly. Spinning reserve. Spinning reserve. What does it mean by spinning reserve? So here, let's say at 0 second, traditional power plant trips offline unexpectedly. Trip offline, then the battery will immediately support. The battery will immediately supply power, right? While the backup power plant, the backup power, okay, the backup power plant, the other spinning or non-spinning reserve support, and then replacement reserve. So because the battery can provide instantaneous power, imagine hydro turbine, a hydro power plant, okay, huge rotating machine. You cannot immediately make it run 3000 RPM. It takes some time. Okay, you open the, what's the name of that thing? Pen stop or something. You open the valve, water comes. It takes time for the generator to turn and provide power. It cannot happen instantaneously. So this is when the battery function discharges instantly.
By short force.
Yeah, not for the whole like 2 hours, 3 hours. It's just for the while waiting for the backup to come, right? That is function of battery for power generation. This is function of battery still in the front of the meter to support the voltage. So I'm not going into detail of this. So basically the inverter or in the PCS try to inject the capacity power or absorb the inductive power and so on, try to control the voltage stability, the grid voltage. So that is one thing, voltage support. The third one is renewable firming, okay, smoothing the volatile output from solar and wind farm. Okay, because output from solar and wind farm is very volatile, depends on the weather, depends on the wind. If a cloud passes over solar array, so the battery will instantly discharge to ensure the grid receives flat, predictable power curve. Output of the power, okay, output of the PV energy, output of the solar. Alright, very volatile. Okay, but if we have battery, okay, to support during low output and to support during low output, excess will charge the battery. Less output from solar, then the battery will support and so on. All right, we will have a smooth demand. All right. Example case study. What happened in Spain, Iberian Peninsula? Smart grid disruption, April 2025. Happened last year. Large part of Spain and Portugal lost power. Origin was traced to a voltage fluctuation. Due to voltage fluctuation, you see here, this is the supply and said then suddenly about 12 p.m. 12 p.m. because of voltage fluctuation, the system cannot maintain the frequency. Then suddenly the whole grid lost power. All right, happened last year. Right, around 12 p.m. You can see the voltage not stable again. So the greatest enemy of such an interconnected grid is an unstable frequency. You have a lot of solar, you have a lot of wind, which is good, renewable, decarbonization and all. When the frequency changes too quickly, plants cannot respond in time. And when it's oscillate wildly, the maximum values can exceed the threshold that shut down disconnected part of the power grid. When the rest cannot support, the whole things collapse. So this is problem that we want to solve using battery. Now, behind the meter, right? Okay, we'll focus on these two only. Behind the meter, the battery can help or support us in peak shaving and energy shifting. Only these two. Alright? Peak shaving and energy shifting. So, okay, the problem, commercial bills include a demand charge based on the highest 15 minutes kilowatt peak hit during the month. For Malaysia, it's 30 minutes. Alright, demand charge is based on 30 minutes. Every 30 minutes, what is the highest amount of power required from commercial consumer. TTM 30 minutes, 30 minutes, 30 minutes within 1 month. What is the highest demand? So they will charge us about 90 ringgit per kilowatt. So we want to reduce that one. How to reduce the peak? By using the battery. So battery monitors the load when heavy machinery turns on, because usually induction motor you turn on like the starting current capacity is how much usually the starting current? I think
70.
No,
7 times.
7 times. I was about to say 5, 6, even 7 times. The starting current, you turn on the machine, induction motor, starting current goes up to 7 times, very high. So this is demand, maximum demand, right? So we can control by control or reduce the peak, shave the peak by using the battery. That is one application behind the meter. Another application is energy shifting. Time of use arbitrage. This is again charge the battery when the energy is cheap, discharge when the energy is expensive. Okay, high peak demand. So we want this is in kilowatt. This is in kilowatt. So every kilowatt is 90 ringgit. UTHM is about 6,000 kilowatt every month. 5,000, maybe 4,000 during semester break, right? So 4 to 6,000 times 90 ringgit. So we want to reduce that. So to reduce that is by this is above this is supported by battery. Battery will support. All right. And then time of use optimization. So right, when the price is cheap, charge the battery. When the tariff or price is high, you discharge the battery. The battery supports the consumption here. That is the type of use or arbitrage. So again, value stacking schedule, single application value justifying as capital cost. Okay, you don't just purchase battery for one application. You have to figure out if primary objective is to capture cheap off-peak rates, but if the battery is already fully charged, you're not going to charge this. But second option it can use is to provide frequency regulation if market require. So please consider not just for one option, one application, but other application as well. Macro grid, so mission critical facilities, for example, another application, hospitals, data center. Maybe you haven't not think about this, but military base, very critical equipment. Maybe Prime Minister office, you cannot have outage, right? So best provide uninterrupted backup power without relying on diesel fuel, right? Islanding mode, solar plus storage synergy. Okay, you have solar, store the excess power, right? A lot of application. Alright, we're almost finished. This is learning activity number 3 before we recap module 3. Alright, so go to your learning sheet. Try to do this exercise. Situation. If you have a factory and you are managing a 2 megawatt, this is the power rating, 4 megawatt hour is the capacity. utility charge a massive $25 per kilowatt demand charge based on your peak load. And the factory, your factory, you can predict usually it will spike to 1.5 megawatt, usually between 2 p.m. 3 p.m. when the certain heavy machines operate. 1.5 megawatt. So, what is your operational strategy for this situation to save the money, bill utility? How much energy will be depleted from the battery to cover this 1 hour of spike? And what time should the energy management system software program to recharge the battery from the grid? Okay, give yourself 5 minutes to think about it. Alright. Kilowatt peaknya. Dulu sebelum kita ada solar, dia boleh sampai 8. Tapi dia ada solar, dan peaknya terus sikit. Kita charge by grid, tapi dia mesti ada cakap dia. Tapi grid itu sendiri sambung dengan solar. So mungkin ada yang datang daripada solar juga. Kalau kita charge masa hujung minggu, tengah hari, mungkin ada dalam solar. Tapi kalau tak ada kelas, tapi hari bekerja, kita masih tak cukup solar. Aircon bukan, tapi dia ada kontraktor yang datang pukul berapa? Pukul 7.30 on chiller, 5 ke pasal ada off chiller. Tapi hari bekerja, tak ada belajar, kita masih tak cukup solar tak cukup. Ada cuti juga. Okay, you can actually go to the next page.
That's good. This task.
This is actually, yeah. Since the battery features 2 megawatt, okay, you want to discharge this much, then 37.5%, right?
So it's like a range from 2 to 4 or what?
This is the power rating. It can, like I said, your phone charger, 20 watt, 100 watt. But if it can discharge power 2 megawatt for 2 hours, continuously discharge for 2 megawatt for 2 hours, then 2 times 2 is 4 megawatt hour. So meaning that with this capacity, you can supply 2 megawatt for 2 hours.
So it's the
or
total of the energy that we can purchase.
Or 1 megawatt for 4 hours.
It's the same.
Or yeah, it's the same. Or 0.5 megawatt for 8 hours. But it cannot give output 4 megawatt for 1 hour because it maximum is 2 megawatt at one time. Right?
This one is peak shaving.
Peak shaving, yes, correct.
This one is
1.5, correct? Because only happens for 1 hour.
This one
Yeah, I should give you the time, right? So peak hours. So for third question, you can imagine Malaysian situation. Peak is between 2 to 10 p.m. 2 to 10 p.m. So charge during off peak. Alright, I think let's just continue with module 3 recap. So learning outcomes for this third module is we want to understand these two things. What is the operational strategy of the front of the meter? And then what is the operational strategy for behind the meter? It's straightforward. Front of the meter, we have learned three things, right? Voltage stability, like we've seen in the Spain case, all right? Integration of renewable energy, and then the third one is for hydropower plant, for example, speeding reserve, suddenly outage. Okay, before we can give backup, battery will support instantaneous power. Okay, so that is the front of the meter, utility side. Behind the meter, in the local building or factory, right? In the example, in the learning activity, is for peak shaving, and then for energy arbitrage, charge during cheap and discharge during expensive. Okay. And then finally, module 4 is sizing, degradation, and economics. I think about sizing and degradation, we have learned something a bit previous slides, previous modules, but let's go into detail here. So we have 3 learning outcomes in this module. We need to calculate the energy requirement. How big is the battery that we need for our purpose, our application. Second is to understand the degradation of the battery. And third, to estimate costing of the battery. Okay, because when we talk about battery, it's not just battery, something else as well. Alright? Energy requirement, degradation, and costing. So, first we need to understand power. I think you asked the same question just now. Power and energy, kilowatt and kilowatt hour, or megawatt versus megawatt hour. Alright? So the most common sizing mistake in battery design is conflating power delivery with energy storage capacity. Usually you will see these two terms, these two numbers in battery. Okay? So for example, if we try to use analogy of water tank, store water in tank, power is the width of the pipe. How big is the pipe? How much water it can support or give at one time. Alright? So power governed by the inverter PCS. Alright? Next is energy. So energy is, if you can imagine, water is the size of the tank. How much water it can store, how much energy it can store, how much water it can supply to your house. Depends on how big is the tank. So the energy, megawatt hour or kilowatt hour, is the value that tells you how much energy it can store. Alright? Right, how long the power can sustain before running empty. Right? This is where we need to understand the C rate. Okay, C rate is defines the speed at which okay. Right. So C rate defines I think I said C rate. The computer thinks I said C rate. Alright, anyway. C rate defines the speed at which a battery is charged. Okay, speed of battery is charged and discharged relative to maximum capacity. I think previously we have learned about 0.5 C, right? So 1 C rate is this 1 megawatt power, and the energy is 1 megawatt hour system. So discharge 1 megawatt power within 1 hour. 0.5 C rate is 1 megawatt slash 2 megawatt hour. It can be like 10, 20. It's just you divide this value divide by this value, you get 0.5. 1 divided by 1, you get 1. 2 divided by 1, you get 2. It's just okay, this value. Typically we'll see 0.5. This is typical, very common. Yeah, common for peak shaving. So 1 megawatt of power discharged for 2 hours, then you have 2 megawatt hour. 2 C rate is 2 megawatt divide by, not divide, okay, this is not divide. 2 megawatt, 1 megawatt hour. So the battery can store 1 megawatt hour, but it can discharge or charge very quickly, right? Discharge full capacity in 30 minutes. So this basically the C rate depends on your application. Going back to the previous module, if your function or your application of, let's say, power generation, hydropower plant, suddenly loss of power, outage, you want to have backup. Do you use 1 C rate or 0.5 or 2 C rate?
2 C.
Because you need that quickly,
Very fast.
a lot of energy. You're not going to use this for 1 hour, 2 hours. It's just for instantaneous for 30 minutes, okay, before the backup comes. So in that application, you use 2 C rate. And for also fast frequency regulation. Okay, suddenly the cloud cover, like in the Spain case, happens just for very quick. But you need to support at high power. Alright. Alright, so C rate, low C rate, longer life, higher efficiency. High C rate, more heat, faster drain. Of course, your capacity is very low, but you want to discharge very quick. You need that power very quick. You need that power very quick, very fast. So the chemical reaction to store and discharge the energy is very quick. So in terms of thermal stability, is quite dangerous, right? Okay. More heat, faster drain. So in that case, you have to figure out the battery you want to design, you want to purchase. So you have to focus on the safety because for this function, for 2C rate, right? Because you produce more heat. Faster drain. So operational limit, depth of discharge and around trip efficiency. Nameplate capacity on the spec is never fully usable in real world, it's just a number. We must derate the system based on physical and operational limitations. So this is important, RTE. When you go for purchasing new battery, one of the things that you need to check is the round trip efficiency. Basically efficiency, okay? Basically it's the efficiency of the battery. So let's just go one by one. Depth of discharge, the percentage of the battery that's actually cycled. A system might be software locked at 90% DOD, so it will not, you cannot charge to 100%. Okay, so restricting DOD exponentially increase the life cycle of the battery. So in this case, you don't charge it to 100%, so you can extend the life of the battery. Okay, depth of discharge. So sometimes the system they lock it to 90%. Okay, there is another reason because if once it's reached 90% of charge, you want to charge to 100% of SOC, then extra 10% of SOC when you want to charge, it requires more energy actually.
It will take longer time.
Take longer time, high power to make it 100%. Alright? So sometimes the system might lock at 90%, you cannot 100%. So don't expect when you want to have 10 megawatt hour of battery, you will get the 10 megawatt hour. Alright? So next is round trip efficiency. When we talk about round trip means fully charged, fully discharged, fully charged, fully discharged. So one cycle. For one cycle, to charge fully and discharge fully, that is one cycle. How much energy you get? And then how much energy you need to charge? Okay, so for example, this battery, this battery can charge 1 megawatt hour of energy. Can store 1 megawatt hour energy. But do you think it use 1 megawatt hour of energy to store this? We have to take into consideration energy loss in the cable, energy loss in the transformer, right? Energy used to cooling the battery as well. All this other additional energy to make it have charge to 1 megawatt hour. So there are other energy. So energy loss during during AC/DC conversion, auxiliary cables. So typically 85 to 90%. So to get 10 megawatt hour of the battery, you might need to charge it 11.5 megawatt hour from the grid. So, right? Because that 1.5 megawatt hour is lost heat in the PCS, loss in the transformer, loss in the cable, energy required for the cooling. Okay. So RTE is very important as well. And then usable energy, nameplate energy times DOD limit times RTE. Okay, 10 megawatt, yes, and then limit cannot charge to 100%, only charge to 90%, and then the RTE, what is the RTE? So that is the amount of usable energy actually. Alright, degradation, battery aging variables. Again, the degradation of the battery, calendar aging, due to calendar, even though you not idle, not operating, it still can slowly degrade. Cyclic aging, wear and tear resulting from the physical act of charging and discharging. Charge, discharge, continuously charging and discharge. Okay. So charge, discharge as well, and also aggressiveness of the serial use. Discharge at 100% full power, right? Discharge or charge at 100% full, and will affect the degradation of the battery. I think one of the things that you can consider to manage the battery is to operate the battery if possible during night time, because the temperature is much cooler, right? In leisure case, in leisure case, I'm not sure how big is the difference. I've never seen any study on that.
Ours sometimes 45 temperature.
45.
Yeah. Sometimes 43, 42, 44.
Okay.
But here in Malaysia, highest 33.
Yeah, 30 plus. And imagine inside the container it must be much hotter, right? In fact, when you select the battery, the container, because the container is fixed, 20-foot container or 40-foot container, the size is fixed.
Yeah.
You cannot change. You cannot have 24-foot container because the size is standard, right? But depends on the design. The same size container can have higher power, more energy, basically, more energy, if it has better cooling system. Like we have in UTHM, it's a liquid cooling. We have liquid cooling, so it's 5 megawatt hour per container. But from the same manufacturer, different design, air cooling, so no aircon, it's not liquid cooling, it's just air cooling. I think if I'm not mistaken, it's 4 megawatt hour. Okay, with the same size. So you can increase the energy density, even though it's same lithium ion, you can increase the capacity by the cooling system, better cooling system. Right. So cooling system, good cooling system can improve the degradation. Okay, reduce the rate of degradation. You have good cooling system, right? 100%, the system degrades over time. Over time due to ACI layer growth. Most commercial systems divide end of life or trigger warranty augmentation when capacity drop below 70%. Okay, 70% state of health. Right? Of course, you can still use it. Still can store some power, but yeah, maybe you have to add more, right? But usually after 15 years you will have more buildings, right? But maybe in terms of the investment, by year 6 or year 9 or 10, it has covered your investment. That goes to the third learning objective of this module, which is the costing. So the total cost, let's say 10 million for example, 50% goes to the battery modules and the packs, just the battery. Half of it goes to the battery, which is still expensive. The most expensive is battery and the safety as well. The risk is here. 20% usually goes to the PCS or inverter, the electronics, right? The electronics. 50% usually goes to the engineering, procurement, and commissioning. Okay, the process, all this process, installation as well, 50%. So the transportation, all the works to install, right? And then 50% goes to the balance of plant, energy management system, and safety. Okay, so all the cables and so on, energy management system, the computer, the safety, all the fire alarm panels, all this, right? That's the breakdown for the cost. But of course, if you ask me personally, I think battery technology is still still has a lot of improvement. Right? Maybe after this new material, new chemical, like I said earlier, Japanese is trying to explore. I think integrated energy storage chip, something like that. Have you heard? This is now they try it on an electric vehicle. Can go 1,000 kilometers, charge very fast. So I think in terms of the battery technology, the electric vehicle will drive us on because like in terms of energy storage for utility, right now we are not that critical on the size, right? But for electric vehicle, I want to do 1,000. I want to charge very quick. So this is where the most important driver goes. Yeah, to improve the technology of battery. All right, finally, let's do 5 minutes 10 minutes, 15 minutes discussion before we recap this training session. So in this activity, you are required to develop a battery energy storage system for a factory. Okay, again a factory. The same factory, I suppose. The load analysis dictates a need for a 2 megawatt/4 megawatt hour system. The system to be locked at 90% depth of discharge to preserve battery life. Okay, we don't want to charge to 100%. And the round trip efficiency is 85%. 50% goes to the energy loss. So please discuss among yourself what is the C rate of the system, calculate the usable energy, how much energy, and then this is the calculation. If the demand charge savings 20,000 per month, how many years will it take to pay back the estimated capex of 1.5 million? Okay. Capital investment of 1.5 million to purchase the battery, but the saving is estimated 20,000 per month. Ignore OPEX, operational costs, and degradation of the basic model. Just calculate the return on investment.
Ini tengok itu api. Kita belum sen. Jadi dia ada loss. Sudah lebih sudah satu liter.
Oh, this 4 megawatt hour. 4 megawatt hour, but the round trip efficiency is only 8.5. So actually you are getting 3.4. You're getting 3.4.
Dia itu bisa
Oh, okay.
Disebabkan terus 90%. Kan dia cap dengan 90%. Terus kalian nanti dia ada masuk nanti kan untuk Baik. Kalau di itu bos masa hari itu dia jadi apa tengok dia charge dia capacity 4 megawatt hour dan kemudian dia charge to 90% saja. Jadi ini memang faham. Dan tadi itu dia apa untuk maksimum kan itu.
Oh ya betul.
Dan nanti kan itu luas. Jadi maksimum balik dan kelebihan di bawah
Tidak discharge.
Şamba, insan ne biçim bir amor bir
Okay. So that 90% less of discharge, the question means that log at 90%, right? Log at 90% means that it can discharge until 90%. So you cannot use the remaining batteries energy. You can only discharge up to 90%. That's the what it means. 90% less of discharge. Okay, to protect the degradation, of the battery. Okay, you can discharge, but 90% only. So 10% you cannot use it.
So even when we use our phones, if the battery says it's 0 or 1%, it's still over 10%, the actual rating.
Good question.
Because when we recharge it, it should have some type of energy to pass up.
Yeah, yeah, I think so. Maybe it's just in the screen it says 0%, but the moment you plug in to charge, immediately some energy there. I think otherwise you can all the data is gone.
Yeah.
But yeah, that is for phone, maybe different application. But this is for the battery. So in this case, 90%. You can discharge 90%. So that 10% is to protect the battery degradation. I think it has to do with chemical, right?
Yeah.
If it's drains, I don't know. I try to imagine like if it goes to 0%. Completely dry or something.
Yeah.
Right? So really, because of the chemical composition, unless we can invent new type of battery that 0% still can charge it back to 100%. I think even like for example plastic you bend it until at one point you cannot make it straight again. You reach to a point that you cannot go back to normal. Something like electricity. Right? Alright, so I give you I think 5 more minutes to discuss on that. If you need to go to the toilet, please go. We have to make it 3 hours.
Okay, still have 1 hour.
I don't know. I think it's not bad. 5:15 or 5:10. Check. Yeah, please.
Victor, what about the activity of the second module? Activity of the second module.
Yep, second module. And first one.
This one, this is the second one, right?
Uh-huh.
So
That is a state of charge and state of health. To 85 degrees Celsius, when it reaches a certain temperature, it's overheat.
the degradation is become more, right?
Uh-huh. In this case, it's not about degradation anymore. This is like thermal runaway means like it will continue and there's no returning back. So it will continue to fail. I think at this point, when the cell starts producing gas, then it's like the cell is already bad.
So the medium of the rapid degradation is the heating, right?
Uh-huh.
So it goes down until 75% only in 1 month due to what?
No, this is just example.
Oh, example.
Yeah, it could be due to like MITE, that one, mechanical, internal, thermal, electrical.
This degradation, it causes the heat, not the heat causes it, right? Which one?
The heat can cause degradation of the battery. Sebelum ni pernah dengan UT di training.
Apa?
Oh, terkenal lah. Tapi dengan apa nama HRD tu tak?
Masih itu belum.
Oh.
Ini untuk dapatkan HRD itu kan. Tapi saya kenal lah.
Oh, okay. Dulu masa yang biodiesel ya,
Ya.
Sekarang tak ada lah kan training biodiesel.
Kalau kita nak dapatkan cicil obitunya terlalu mahal, mintanya 5.000.
Berapa?
5.000.
Yen. Kan kursus je.
Kursus itu at least 5.000, cicilnya je 3.000. Oh, overseas dia punya.
Overseas.
Itu yang.
Tapi yang dekat Johor dia dah tak ada.
GPTC-nya yang apa itu tak ada dia.
Oh. Tapi masih bagi training tu, biodiesel masih pakai.
Masih. Jadi kita cuba nak ring yang untuk 500 tu.
Mana?
Yang untuk budak belajar degree bayar 500 tu.
Oh, okey.
Kita nak kurangkan jamnya lah, jam kursusnya tu.
Kita ada motor, induction motor semua kan?
Pump, ada pump.
Motor pump kan?
Itu yang aku cakap kalau nak ni suruh jumpa tu kan?
Yang mana?
Yang aku cakap nak masukkan apa tu? Training itu kan? Yang kau cakap
dulu. Tak penting kan? Nanti boleh bawa lah. Kita untuk pelajar yang 500 pun boleh. Kan? At least itu tiap-tiap tahun ada kan? Kita confirm jalan.
Yang janji kalau fakulti kita lepas, kalau yang mechanical dia kena ada job yang company luar tu.
Oh, tapi ni memang dia punya syarat dia memang nak kena company luar kan?
Tapi hari itu kita lobby nak dapat lah ini katanya aku tanya kalau tempat kita pun sebenarnya tak salah wajib dulu.
Ya.
Itulah yang kau nak masukkan title untuk training itu kan? Aku cakap aku suruh hubungi ini kan? Nanti dia buatkan itu HRD-nya itu. Tidak ada license untuk buatkan HRD itu yang diberlakukan untuk ini. Aku ada assessor dengan kawan yang biodiesel itu kita dapat assessor yang dari luar negara itu masih jenis.
Oke, itu.
Gitu. Itu assessor itu.
Tapi kursusnya mahal kan?
Tapi memang registered Scotland kan nanti kalau dapat cicil itu Kalau in case memang soal itu sekat lah ini kalau mudah juga kerja buat kena hati itu. Kalau tak ada masuk kerja kena training dulu. Kamu nggak ada training. Satu kalau ada training satu. Namanya kalau ada competition 10 orang, kalau dia ada sijil itu kemungkinan besar masuk itu.
Sangat terjang, maksudnya bekerja situ agak orang.
Lah kaji yang sendiri ni lah je. Kalau kaji yang sendiri pun kita sampai saya di jam.
Alright, so for this learning activity, can I have someone to tell your answer for the first one? What is the series of the 0.5? Yeah. 0.5 is the series of the system. So basically it's not for the frequency regulation, so it's like peak shaving, right? Just like in the, of course it's a factory. It's a factory, you need peak shaving. So 0.5. If it's 2C, then it's wrong, right? How about the usable energy in kilowatt hour available for dispatch on day 1? So mean like the first day, new battery. What is the any answer from you? Mujahid?
360.
300? 3,000 or 300?
360 kilowatt hour.
3,600, right? It's 1,000. Thousand, right?
Yeah.
Okay. Okay. Because of the depth of discharge 90%, even though in the nameplate is 4 megawatt hour, the system lock, you can only discharge 90%. So you cannot use that remaining 10%. So the usable energy is actually 3,600 kilowatt hour or 3.6 megawatt hour, right? And how about number 3?
Number 3 is 75 years.
Huh?
75 years.
7 point?
How 75 years?
6 point.
Let me check your answer.
Because you said that is 1.6
Million, okay, that is the.
So this is so if you divide, you have the.
No, but the 20,000 is monthly, not
Alright, this is month. This is month. So 75 months. Yeah, okay, convert into years.
Month, yeah.
Right?
Yeah, 75 months. That is
So convert into months is.
multiply by 12. Then it will become 6 year, 0.25.
6 years.
6.25.
25 is 3 months. 6 years and 3 months to pay back the capital expense. Okay, you invest 1.5 billion, right? But ignoring operational expenditure, okay, and degradation. Forget about that. Too much to calculate. Simply, you spend 1.5 million, install the battery, everything. You can save. If you save $20,000 per month in 6.6 years, 3 months, it can pay back or cover the investment you made, right? So if you pay back in 6 months, so make sure when you design the batteries, your warranty state of health higher than that. Alright? State of health is higher than that, 10 years, right? because they degrade very quick before you can return the investment.
What of the behavior of the battery in simulation? Does it also apply to, like, now students, most of us do simulation already. So what about the behavior of the battery, maybe in terms of modeling? That is MATLAB and all that.
That one cannot answer in terms of modeling. I haven't done the manual part. This is just like simple calculation, rough estimation. Even though in modeling, now in actual situation, you don't charge to 90%. 100% goes to 90. Discharge 90% or SOC make it 10%. Because every day the consumption is different. And then you reach weekend. Maybe weekend you don't have maximum demand. Maybe weekend you don't use it at all. So it depends on the battery management system as well. Like for example, let's say this is your load profile, okay, for your plant or for your office, right? Let's say this is 8 a.m., this is 5 p.m. Right? You want to cut the maximum demand. So how do you operate the battery management system? The battery. Okay, this is 5 megawatt, the maximum demand. At 3 megawatt, you tell the battery once the consumption reach this, you immediately discharge. Right? So this is amount of energy use that you need from the battery. Maybe on certain day, lot of people, you have event. This is now 6 megawatt. Okay, but you still set the battery to operate when it reach 3 megawatt. So now the energy is more than this. Maybe this is you can calculate. This is 2 megawatt. This is 2 megawatt. 2 megawatt for, let's say, 5 hours. So that is 10 megawatt hour. This is here 3 megawatt. Let's say same thing. This is 5 hours. So this is now 15 megawatt hour. So you need bigger battery. Because you set the battery to operate. Once it's reached 3 megawatt, you read from the utility 3 megawatt. Okay, enough. I want to use battery. Right. So now the battery you need 10 megawatt.
Demand increases.
Yes. So in that case, the life cycle, depth of discharge, everything is different because every day the consumption, how much the battery requires, every day is different.
Balance.
Because you cannot, for example, if your battery is 12 megawatt hour, okay, by the time it reach here, you still have 2 megawatt hour balance left. But in this case, 12 megawatt hour, maybe after this, your battery goes to 0. Yes. Then from the grid, this is coming from the grid. You need to take from the grid, from the utility. This goes to 0, battery goes to 0%. Or 10% because knock. So you still being charged for the maximum demand. So it's the way you control the battery is also important. So in terms of modeling, I think if you want to do modeling, you have to take into account the load profile every day. Worst case scenario, lot of event, university we have convocation, everything turn on airport, especially during December. December we have semester, class, everything, also convocation, right? So of course we can calculate 20,000. This is alright, just for the sake of calculation, but in real case, maybe more saving, maybe less saving. Alright, so module 4, let's recap for module 4, key learning objective, how to calculate energy requirement. I think we are now familiar, know how to do this. How much the megawatt hour, the C rate, and then the degradation, okay, life cycle, and then the number of days, okay, even though you are not using the battery, it can degrade, okay, and then how to estimate the cost of battery and storage. 50% of the cost comes from
50% comes from the
battery itself.
rack,
Yes, battery rack, the battery cell itself, right? The rest, the all the
20 for battery.
yeah, engineering, procurement, commissioning, and so on. So 50% is come from the battery itself. So okay, we are come to the end of our training session. Let's summarize and recap. Alright, so let's look back at the key milestones achieved across our 4 comprehensive learning modules. We have 4 learning modules. First one is on the physical battery architecture, cell type, lithium iron phosphate, and MC is nickel, manganese, cobalt, or nickel, cobalt, manganese. So basically it's the same thing. So chemistry, the three attributes of this. And then the second module is battery management system and the safety. Okay, we learn two new keywords: state of charge, state of health. Right? And then also another keyword, thermal runaway. Start releasing gas, and then start fire, heat, and the one is start, there's no return. Okay, alright. So, and how to mitigate. Okay, what are the sensor? Gas sensor, heat sensor, smoke detector, alright? The third module is grid application, front of the meter FTM, behind the meter FTM. Front of the meter, we have three examples. Okay, power generation, frequency regulation, and renewable integration. Behind the meter, we have two examples, peak shaving and energy shifting by chip cell charge when it's cheap, discharge when the price is expensive, right? And finally on the sizing and economic. So make sure you know the sizing calculation, the C rate especially, and then the degradation factor, and then finally the cost, the capital investment. 50% of it come from the energy storage, from the battery, right? So basically, learning points. We have 4 learning outcomes. 4 learning outcomes that we want to achieve in the when we first start this training session. Each of these learning outcomes, we have 4 learning modules. Alright, so now we have identified the primary physical component of modern BESS, LFP, and nickel, manganese, cobalt cell chemistries. Okay, I think we have achieved our first learning point.
Yes.
Right? Second learning point is to evaluate battery management control, state of charge, state of health. Right? This is the battery management system, the brain of the battery. Alright? It's very important. Right? Mitigation strategies for thermal runaway. I think we have achieved this. Number 2. Number 3 is the grid application. Once we have understand the battery structure, we have understand the battery management, the safety. Now connect this to the grid. What is the application? Behind the meter, front of the meter. Right? We have achieved this outcome, objective. And then finally on the sizing and economics. Right? Do not oversize. Okay, do not oversize, but don't under design as well. Okay, you spend 1.5 million later to find out you cannot. Yeah, but I think for peak shaving, you still can save. You cannot, if you cannot save 20,000, at least you can save 50,000. If you're under design, all right, still can do some saving, but we have to calculate again on the. We have to recalculate on the payback period. Can you still achieve 6 years? Right? Because remember, 50% is the battery.
Yeah, so the battery consumes much, so the
Ah.
battery cannot last long.
Yes,
It
yeah.
has not been achieved.
50% is battery, cannot last long. 20% is all the energy management, safety, the cables, installation, and the rest. If you increase the capacity of the battery, maybe the cost of the installation is still the same or not much different. Maybe add a bit, right? Can you imagine?
Yeah.
Because you still need to pay for the installation. Might as well add more to add more battery capacity. So something like that, you have to figure out the best situation. Alright? Plus the routing efficiency, you can 10 megawatt hour of the energy usable, actually you need 11.5 because you have some losses. Alright, so that degradation and the cost and so on. I think that's all. We have covered all this training session, 4 modules, 4 learning outcomes. I believe from your feedback, from your response, I think we have achieved all these learning outcomes. Thank you for your time. Thank you for your interest on this session, this training. Hopefully next time we can arrange another visit to see the actual battery. Right? So to do that, to give me some time to find out when we can shut down the battery, because we need to open the rack so to see the details, the battery management system of the cell level, the rack level, module level, and so on. All right. Thank you again. So hopefully see you soon. All right.
So why the cabinet cannot